Then how is the diffraction pattern obtained in X-ray experiment related to the crystals that causes the diffraction? X-rays interact with the electrons on each atom and cause them to isolate. The isolating electrons serve as a new source of X-rays, which are emitted in almost all directions, called scattering, when atoms and hence their electrons are arranged in a regular three-dimensional array, as in a crystal. The X-rays emitted from the isolating electrons interfere with one another. They could cancel each other, or in some cases they could add up to be strong X-rays. Such add up X-rays could produce diffraction patterns on detector. Initial X-rays passing through protein crystals produces this kind of diffracted beam. The production of diffracted beam could be explained by Bragg's law. Bragg's law tells that diffraction by a crystal can be regarded as a reflection of primary beam by sets of parallel planes, rather like a set of mirrors through the unit cells of the crystal. Different sets of parallel planes can be arranged through the crystal so that each corner of all unit cells is on one of the planes of the set. The diagram shows in 2 dimensions 3 simple sets of parallel lines: red, blue, and green. By using any lines, we can apply Bragg's law. Bragg's law relates 3 things. In this diagram, the distance between 2 lines, d, and the angle of incident light, theta, to the lines, and also the wavelength of incident X-rays, lambda. The relationship between them is 2d times sine theta is going to be lambda. In this hypothetical 2 lines, imagine 2 lines as mirror. X-rays that are reflected from adjacent 2 planes, 2 lines, travel different distances. Upper X-rays coming here and hit at this position and reflected. Lower beam coming parallel to the upper one and hit at C point and reflected. Lower beam travel more than upper one by amount of B, C, D. How can we calculate the distance of B, C, D? By geometry of this relationship, that could be simply D. The distance of 2 lines times sine theta. You can figure out easily. So actually, the difference in pathing distance between two lines will be BCD. That will be 2 times d sine theta. Okay, that must be exactly match with the wavelengths of X-rays used in this experiment. In that case, two beams could add up each other to be strong. Okay? And by using Bragg's law, we could obtain D values, the distance between two adjacent lines, because two other parameters could be determined. First, theta could be obtained by geometry of the experiment. So here you beam X-rays, crystals position here, and you obtain the actual diffraction spot on film, which is located apart A from crystal, and the angle between the lines formed by crystal and the spot and the initial X-ray beam is called 2 theta. Tangent to theta in this case will be R, the height of spot, over A, the distance from crystal to the film or detector. Because we know R and A, theta could be figured out. Why 2 theta? You imagine the picture we used in previous slide. Two hypothetical lines lined against initial X-rays and the diffracted beam, where both has identical thetas. Okay, then this will be 2 theta. And second parameter in Bragg's law, lambda, is wavelength of X-rays you used. We know from the beginning the wavelength of X-ray we use for this experiment. Simply, theta could be obtained by the geometry of reflection angle, distance, and height. And lambda is just simply wavelength of X-ray we use for this experiment. Meaning what? We could determine set D, the distance between two parallel lines, adjacent lines. Then you might ask why there are so many diffraction spots on detector. Simply, there are so many lines possible. You can make green here, passing through the corners of unit size. Another simplest diagonal lines could passing through here and here and here, something like that. Such lines are produced so many ways that could function in producing so many different patterns. Of course, to obtain more spots, we must change the position of crystals by using goniometer. Can get so many spots. For example, myoglobin, which is 154 residue long, it has about 1,500 atoms that could give approximately 20,000 spots. So by using this spot, diffraction spot, how can we extract actual molecular structure of this protein? To get information about such a structure, we need three things: phase, amplitude, and wavelength. Amplitude could be obtained by measuring intensity of diffraction spot. Wavelength is representing the wavelength of X-rays, so that we know from the beginning. The very ambiguous thing is phase, so-called phase problem. In this diagram, you can see three things: wavelength, amplitude, the height of this radiation, and phase is the position of moving radiation. Two radiations are different in terms of phase. Right? Initially starting here for the yellow, positioned here, but the pink is positioned here. They are different in phase. So how can we determine the phase? It's not easy to determine. There are several ways we can overcome this problem. The first one is the direct method. This could be applicable for small size of molecules. It's not possible for the complex molecules like protein. And second technique is called multiple isomorphous replacement, simply MIR. It's just based on the identical molecules, but they are different in terms of some additional small number of heavy chains.